Okay, so in this movie clip, let me explain how to solve the example on a photoconductor. So now let's consider a sample of silicon which is doped with a 10 to the 16 boron. So I guess that this silicon is a p-type, right? And with recombination lifetime is 1 microsecond. So once this is at p-type, so electron is injected into this silicon, or a certain excess electron is created in this p-type silicon material, that minority carrier electron would be recombined with the hole within a 1 microsecond. So on average time to become annihilated with a hole, 1 microsecond is necessary on average. Okay, so it is exposed continuously to light. So which means this light is breaking the equilibrium state of these samples at p-type silicon. So such that as a result, electron hole pairs EHPs are created throughout the sample uniformly, I guess. So at the rate of 10 to the 20 per cubic centimeter per second. So every single second per cubic centimeter, 10 to the 20 electron hole pairs are created by light. So in other words, that is generation rate G sub L is 10 to the 20 per cubic centimeter per second. Okay, question number one is, what are P naught and N naught? So naught means at equilibrium. So before uh, this silicon sample is exposed to light continuously, how many holes and how many electrons does this silicon sample have? So here, as described here, 10 to the 16 boron. So acceptor's concentration is 10 to the 16. So the whole concentration at equilibrium state is identical to the acceptor's concentration, because these uh, acceptors would be fully ionized, because acceptor ionized state is kind of shallow trap site, so it is easy to become ionized, easy to capture electrons coming from the covalent bonding, or electrons coming from the valence band, into the acceptor site, which is very closely positioned and placed near to the valence band. So that is 10 to the 16. Okay, and what is N sub naught? Using a mass action law, we can estimate the electron concentration at this p-type silicon material. So 10 to the 16, 10 to the 10 square. So the answer is 10 to the 4. Definitely per cubic centimeter. Okay, all right. So P naught and naught. Very simple. Okay, number two, what are the delta N and delta P? So now it is the silicon sample is exposed continuously to light. So generation rate is 10 to the 20. So GL is, how to understand GL, generation rate. So electron hole pairs are created. So now the minority carrier is, in p-type silicon, minority carrier is electron. So excess electron concentration divided by, its lifetime should be generation rate 10 to the 20. Why is that? Once the electron is created by light, and at some point or at some time, the created electron would be annihilated with a hole. But herein, this example said, continuously light is exposing, this sample is exposed to light continuously, so that another electron should be created. So one at some place, electron is annihilated with a hole. At the other place, the same amount of electrons annihilated at the other place should be created, so that the generation rate 10 to the 20 per cubic centimeter every single second would be kept constant. So that's the reason why I'm using a GL is equal to delta N divided by tau sub N. Okay, from this concept, delta N can be simply obtained that GL times tau sub N. And GL is 10 to the 20 and lifetime is 1 microsecond. So 1 micro means 10 to the minus 6. So that delta N is 10 to the 14 per cubic centimeter. So every per cubic centimeter, 10 to the 14 electrons are available, whatever the time is, because the light is keep exposed this silicon sample is exposed to light continuously so that the total number of excess electron, not electron at the thermal equilibrium, excess electron, in other words, delta N, has been kept by this light. Okay. Then now let's move on to the next solve question. What are P and N? So P is defined as this, right? And N is defined as N naught plus delta N, right? Previously I said delta P is defined as P minus P naught. So using this equation, you can get this. Okay, and what was a P naught? In question number 1, P naught was 10 to the 16. And what is delta P? Because of the charging neutrality condition, if at a certain place electron is excessively created, then in other place the holes are excessively created together because E and H electron holes are created in pairs. Okay, so this is delta N. What was the delta N? GL times delta N. That was 10 to the 14 in the question number 2. So 10 to the 16 plus 10 to the 14. So, that is, 100 times higher than 10 to the 14. So you can ignore this number. And the answer is 10 to the 16. 10 to the 16 is P naught. So that is P. Aha. The majority carrier concentration in P-type silicon sample has not been modified, has not been affected a lot, has not been affected significantly by the light. However, let's take a look at the electron concentration. And nowadays, in the question number 1, that was 10 to the 4, and delta N is 10 to the 14. So, 10 to the 4 is nothing compared against the 10 to the 14. So you can ignore this number, and the answer is 10 to the 14. Okay, so this N is much, much higher than N naught. Okay, but take a look at this number. N is much, much higher than N naught, and delta N, this number is 10 to the 14, but that is smaller than P naught. Okay, at thermal equilibrium, this P-type silicon sample has this amount of hole concentration, and the electrons created by light. In other words, this P-type silicon material has obtained, observed, internally, this electron has been created by the light. Anyhow, for the given P-type silicon material, the electrons are additionally created. But this additionally created electron concentration is much, much smaller than the majority carrier concentration at thermal equilibrium. In other words, majority carrier concentration is not affected significantly. However, the minority carrier concentration, in this case, electron in P-type silicon sample, is significantly affected. Okay, so now you are seeing the number. Question number 4 is, what is the NP product? So N times P. So the author is not asking you to do the multiplication work between N naught and P naught. N naught P naught is, Ni squared. That is a mass section law. But now the author has asking you to calculate NP product. So this is not value. Okay. So N is, 14 right here, and P is 16. So the answer is 10 to the 30, which is much, much higher than 10 to the 20, which is Ni squared. Okay, so NP is not anymore equal to Ni squared. Okay, N naught P naught is equal to Ni squared. And here the question is, do we have another equation to make this equation valid? Can we multiply something to complete this equation? We're gonna learn that later in PN junction diode. Okay, but at this moment, let's leave this question mark behind, and let's focus on this. NP is very different from Ni squared as described in this note. Okay, all right, so at non-equilibrium state, N naught times P naught, or no. The electron and hole concentration product is never equal to the Ni square. Okay, the equilibrium state is kind of broken, so mass action law is not valid at all. But N naught P naught itself is still equal to the N naught times P naught is equal to Ni squared. That is always true, but I'm talking about N times P is not equal to N naught times P naught. Okay. This is just only for your information. So if you're interested in deriving and understanding this net recombination rate in general case, then please go to and refer to the appendix of your textbook. Then you're gonna see some more details. But I guess that this would sounds very complicated and it would lose your motivation of studying this solid state physics. So I would skip this single slide at this moment. Okay, that's all for today's lecture, and see you next week. Bye bye.